This will be an introduction to scattering diagrams. And I will follow Greg Muller's user-friendly presentation of the subject. So first, the idea. What is a scattering diagram? The scattering diagram of a quiver Q. We should view it as a geometric device which encodes all the quantum dilogarithm identities associated with Q. Encodes in a consistent way all the quantum dilogarithm identities which we have seen in the last lecture associated with Q. And one technical remark. So technically, we will not be working with quantum dilogarithms. But with a specialization at one of their adjoint action. The quantum dilogarithm itself does not specialize well at 1, because in the denominator of the coefficients there are terms q minus 1, but the adjoint action specializes without any problems, and that's what one uses. Okay. So let's start with finite scattering diagrams. A finite quiver without nodes nor 2 cycles, and I will always make this assumption, and with vertex set, the set of natural numbers between 1 and, I will call this now R, rank, R like rank. And this will be a standing convention. And then I will define the B matrix slightly differently. Then up to a sign it's the same, but Bij is the number of arrows from J to I minus the number of arrows from I to J. Okay, this is just a slightly different convention, which will be useful. Then we consider the algebra R, which is the power series algebra in indeterminates y1 up to yr, with coefficients in the Laurent polynomials in x1 up to xr. And for an integer vector m, we write x to the mth for the monomial in the xi's, the Laurent monomials in the xi's associated with m, and for a non-negative integer vector n, we write y to the n for the monomial, ordinary monomial associated with n. And then, with each non-negative integer vector, we associate a certain automorphism of this algebra, which is induced by a specialization at one of an adjoint action of a quantum dilogarithm, namely the so-called elementary transform. And it's an automorphism of our algebra R. I will define it on monomials. It sends a monomial xm to 1 plus x to the b n times y to the minus n scalar m divided by the greatest common divisor of the coefficients of n. And it is the identity on the y variables. And so here, yes, GCD of n is just the greatest common divisor of the components of the vector n, and n times m is the standard scalar product, n times m I. And then the pentagon identity for the quantum dilogarithm yields a pentagon identity for elementary transforms. Suppose that we have two non-negative integer vectors n and n prime, which yield a scalar product 1. Then the composition of the elementary transforms en prime is also the composition of en prime, en plus n prime en. Okay, and this can be checked directly. Or deduced from the pentagon quantum dilogarithm identity, which is associated with the two maximal mean sequences of the quiver A2. Yes? Yes, thank you. Thank you very much. Okay. Okay, now what is a wall? In real R space, it's a pair N W, where N is a non-zero integer vector with non-negative coefficients, and W is a convex polyhedral cone spanning the orthogonal hyperplane of the vector n. So a finite, the convex hull of a finite union of rays. And each wall has a green side and a red side. The green side is the set of vectors m, the scalar product is with n is positive, and the red side is the set of vectors m where the scalar product with n is negative. Okay. And two remarks. First of all, such a wall cannot meet the strictly positive orthant because the vector n is positive. So since n is a non-zero vector with positive components, the wall cannot meet the strictly positive orthant, and for the same reason it cannot meet the strictly negative orthant. And what happens if the rank equals 2? Well, if the rank equals 2, then such a convex polyhedral cone is either a ray or a straight line. W is either a ray or M or a line or M for some non-zero M. And a scattering diagram is simply a family of walls. family. Not a set, we may have repetitions. D of walls. And then we need the notion of finite transverse path with respect to D. A smooth path. Is finite transverse to a scattering diagram D if it satisfies the following natural conditions. It should not end, it should not start on a wall, and it should not end on a wall. Secondly, it should cross the walls transversely. Whenever P intersects a wall, it crosses it transversely. And finally, it should intersect only finitely many walls. And does not intersect the boundary of any wall. Nor the intersection of two walls which span different hyperplanes. Okay. Now with each smooth path, we take a smooth finite transverse path, P, and we look at its intersections with the walls. And to each intersection, we associate a sign. The sign is positive if the path goes from the green to the red side, plus, and it is negative if it goes from the red to the green side. Okay. Scattering diagram. And P a finite path. Let us consider the sequence of walls crossed by P. Okay. The walls order. Then we define epsilon I. Epsilon I is plus 1 if P crosses the wall NIWI from the green to the red side, and it is minus 1 in the opposite case. We define the path-ordered product associated with P. Well, it's just the composition of the automorphisms associated with these walls, where we take the automorphism if the sign is positive and its inverse if the sign is negative. P, this depends on the scattering diagram, and we compose in composition order This is the opposite order to the one which I used in the previous lecture. That's why we had to change the definition of the B matrix. Okay, and then we define a finite scattering diagram to be consistent. If for each loop we get the identity, the path-ordered product associated with the loop is the identity automorphism. Each finite transverse loop. And then one says that two finite scattering diagrams are equivalent. Equivalent if they yield the same path-ordered products. E P with respect to D equals E P with respect to D prime for each smooth path P, which is finite transverse for both. Okay, let's look at our standard example. We take a two quiver. So the B matrix associated with it will have coefficient 0, 1, minus 1, 0. Then we look at a scattering diagram D in R2 with 3 walls. Namely, the walls are the two coordinate axes. So we take wall E2 and the line R E1. So the normal vector points upwards. And here we take E1 and R times E2, the normal vector points in this direction. So the green direction, I put a little arrow for the green direction. So these are two of the walls, and then there's a third one, namely this diagonal ray, E1 plus E2 R times E1 minus E2. Okay. Yes, so notice that these normal vectors are the three positive roots for the root system A2. And let's check whether this is consistent. Well, the fundamental group is just the fundamental group of the circle. We have to check essentially one loop, but checking one loop is equivalent to checking the equality of the two path-ordered products going this way or going this way. So here, each time we go in the green direction, and then consistency follows from the pentagon identity. Now takes the form EE2, EE1. This is the path-ordered product associated with this path. This is equal to E1, E1 plus E2, E2. Yes, this is the path-ordered product associated with the other path. Yes, since we're always going in the green direction, we don't need any signs here. Okay. So far for the finite scattering diagrams. Now, the interesting thing is that we also have infinite scattering diagrams, which encode quantum logarithm products with infinitely many factors. Okay, and in order to manage these, we need a truncation operation. And for the truncation operation, we look at monomial ideals in the power series algebra. We will define consistency of infinite scattering diagrams by reducing to the finite case, and the reduction is always modulo such a monomial ideal, which will be of finite codimension. So first of all, consistency modulo I for a finite diagram. Consistent modulo I. If the path-ordered product induces the identity in the quotient of R by the ideal generated by I. modulo the ideal generated by I for each transverse loop. P. Then two finite scattering diagrams are equivalent, modulo I if the path-ordered products coincide modulo I, D prime induce the same automorphism of the truncated algebra R for all P finite transfers for both. And now we pass to infinite diagrams. The reduction D modulo I of an infinite possible scattering diagram D well, we simply delete, we remove all the balls whose normal vector corresponds to a monomial in the ideal I. Removing all balls and W such that the normal vector gives a monomial in I. Then a possibly infinite scattering diagram D is consistent if for each finite codimensional monomial ideal I, the reduction is consistent. So if D I is, it should be finite and consistent, modulo I for each monomial ideal, so an ideal generated by monomials, I of finite codimension. And then we have corresponding notion of equivalence to possibly infinite scattering diagrams D and D prime are equivalent if their reductions are equivalent. So if D modulo I and to I are equivalent I for each monomial ideal I of finite codimension. Okay, and the main theorem on scattering diagrams is existence and uniqueness for each given finite quiver without loops and two cycles. Well, this is a theorem with a long history. It comes, of course, from mirror symmetry. It was proved by Kontsevich-Soibelman in the rank 2 case, then by Gross and Siebert in the finite rank case, and then adapted to the quiver setting by Gross-Hacking-Keel-Kontsevich. Each quiver Q, always finite without loops and two cycles. There is a consistent scattering diagram D associated with Q, such that we have the coordinate hyperplanes as walls. There is a wall EI orthogonal, with normal vector pointing in the positive direction. And for every other wall, we have that the vector B n does not belong to W. Okay, and of course now the first example is the chronicle quiver. Let's formulate this as a proposition due to Kontsevich-Soibelman and to Remark. The following is the consistent scattering diagram for the chronicle quiver. Okay, so here the matrix is 0, 2, minus 2, 0. Okay, it looks like this. We have the coordinate hyperplanes, of course, with the green direction being this one. And, well, let me write down the list of the walls. E1 orthogonal, E2 orthogonal. Then for each integer greater or equal to 1, we have a wall k plus 1 with array k. Let's switch. So it looks like this. Discrete set of infinitely many walls. Then, yes, so notice that these correspond to pre-injective representations via the dimension vector. These are the dimension vectors of the pre-injective representations. Then we have for each k greater or equal to 0, 2 copies of a wall 2 to the k, 2 to the k, with array 1 minus 1. So, well, these correspond to certain regular representations. So the ones in the tubes. And finally, we have the post-projective representations with dimension vector k plus 1 k and array post-projective representations, those which in the Ausland-Rating will come right after the projective representations. Okay, so here we have this limiting array corresponding to the regulars, and then we have the another discrete set of this ray is special. It has infinite, this is a wall with infinite multiplicity. All the others have multiplicity 1. Again, the green directions are always like this. And to check consistency, it suffices to check that this path gives the same path-ordered product as this path, modulo any ideal of finite codimension, monomial ideal of codimension. So it corresponds to the ray, I've just, yes, sorry, it corresponds to the ray. We had all so for each, we have this wall which has the same support, but with infinitely many normal vectors. Regular representation. And consistency follows from the infinite identity, which we have already seen yesterday. So here it means that E 0, 1 composed with E 1, 0. This should be the composition of all these elementary transforms E1, 0, E1, E2, etc., then an infinite product, the square of an infinite product, and then the pre-injectives. Pardon? So because we have two copies, yes, it has disappeared, but we have two copies of each of these walls. Sorry, two copies. Yes. Where comes from the two copies, yes?
Where can be outside or inside?
It doesn't matter, no, they commute. They commute, they have all the same normal vector. Now, this contains the whole information on the cluster algebra. There's no time to discuss this connection in full detail, but let me at least give the connection to the G vectors. Okay, so let's fix a quiver. Let me recall the definition of the G vectors. Well, remember we have our n regular graph with root T0. And with each vertex of this graph, we associate a quiver, namely the one obtained from the initial quiver by mutating successively along these edges, along these mutations. So the quiver Q, yes, for each vertex T of the R regular graph, we have the quiver Qt, which is defined recursively. Q at the root, Qt0 is just the quiver Q. And if T and T prime are linked by a mutation K, then Qt prime is the mutation at K of Qt. Then we have the G vector basis. Also associated with the vertex T, G1, T, and to GR. T, this is a basis of the lattice Z to the R. And it's also defined recursively at the root. It's just the standard basis. And at an arbitrary vertex, we define it recursively, namely, if we have a green mutation, then G I T prime is G I T for all I different from K, and G K T prime is minus G K T plus the sum over all arrows from J to K, arrow in Q T of the G J T. And we know that between any two neighboring vertices there is exactly one green mutation, so this defines the G vectors. And then third, we have the C vectors. C vector basis C1, T up to RT, and it's just the dual basis. For the standard scalar product. Since we work with quivers and not with valued quivers, okay, then let's take D to be the consistent scattering diagram associated with our quiver Q. Then we define a chamber of D as a path component of the complement of the union of the walls. Minus the union of the walls. For example, the strictly positive orthant and the strictly negative orthant are always chambers, and they're called the green chamber and the red chamber. So since the coordinate hyperplanes are walls, and since no wall meets the entirely positive or the entirely negative orthant, these have to be chambers. Green chamber, that's the initial chamber. A strictly positive orthant, and the red chamber. The entirely negative orthant. These are chambers. Limited by walls, and no walls pass through them. Then, so then the picture is like this. We have the green chamber. We have the red chamber. Then we have many other chambers. And we say that a chamber is reachable if there is a finite transverse path from the green chamber to this reachable chamber. is connected to the green chamber by a finite transverse path. So in the examples we have seen, all the chambers were reachable, but there are definitely quivers where not all chambers are reachable. For example, the quiver of the once punctured torus. Okay, and now the link between G vectors and chambers. Theorem by Gross-Hacking-Keel and Kontsevich. Namely, we can, for each seed, or for each vertex of the regular tree, T, we look at the cone, the positive cone generated by the G vectors at T. Okay, this is a certain cone. T, and the claim is that this is always a reachable chamber, and in this way we get a bijection between the vertices of the exchange graph and the reachable chambers. Vertices of the exchange graph to a set of reachable chambers. And moreover, the geometry of the chambers reflects the orientation of the exchange graph, namely, moreover, we have a green mutation from T to T prime. Let's call this the cone of G vectors associated with T. We have such a green mutation if and only if the two chambers share a wall. NW. And we pass from T to T prime by passing from the green side to the red side. And moreover, in this case, the normal vector n is just the C vector associated with this green mutation. Well, let me, yes, and so in this way, thus a maximal green sequence for Q corresponds, well, a maximal green sequence is a sequence of green mutations going from the all green chamber, from the green chamber to the red chamber. Yes, this is what a maximal green sequence is, corresponds to a finite a green path from the green chamber to the red chamber. And, well, this allows us to prove Muller's theorem. Maybe you remember. So we have Q with a maximal green sequence. We have Q prime in Q a full subquiver. Let's say with vertices 1 up to V. Okay. Then we have R to the R, and we have R to the V. Our scattering diagram dQ lives in R to the R, and we have a scattering diagram D, consistent scattering diagram for Q prime in R to the V. Between these two we have the projection. And what Muller's theorem says is that Q prime has a maximal green sequence. And the idea is very simple. We simply take a maximal green sequence for Q and compose it with a projection to RV. And this, then one has to check that this does yield a maximal green sequence for Q prime. And it's, for example, it is clear that if this maximal green sequence starts in the green chamber and ends in the red chamber, then this one is also going to start in the green chamber. The all positive chamber is taken to the all positive chamber by the projection, and it ends in the all negative chamber. The projection preserves positivity and negativity. So one shows that I composed with P is a green path linking the green chamber of the scattering diagram of Q prime to the red chamber. Yes, this is Muller's proof. Okay, and yes, so this requires to be checked, but it is not very difficult. The difficult part is the existence and uniqueness of the consistent scattering diagram associated with Q. Thank you very much.